Recordings rolling. It is Thursday, September 4th. So I'm going to try to get to projectile motion. I'll start, guys, finally with projectile motion today. You guys have a new page in front of you. It looks like this. Special questions on one side, like six situations, and then they each come with a bunch of little questions. On the back side, ooh, I see some cannons on some cliffs, like lots of some cannonballs. Hey, you guys see this projectile motion right here? Like this projectile? Okay. So this is still kinematic motion. Okay? So for the next few days, as we're doing these projectiles, it's the exact same formulas. There's no new formulas for the next few days. Everything we've just been using. Okay? But now you have to keep track of two dimensions. So what's going on horizontally, what's going on vertically. So I will walk you guys through how to look at this paper. This class goes on. But yeah, I got some posters, got some demos, got some examples. Okay. These puzzles, I'll pick up from you guys Thursday, September 11th is due date on these. We'll work on some of these on today and tomorrow. Next week, I'll have at least one projectile lab, but I'll fill you guys on that later. You know what activity I've been trying to get to that I haven't yet, but I'll put this in at the end of today. It's about the last 15 minutes or so today. Is this reaction time lab? Now, this is still part of linear motion, but actually there's an application that's just going to link exactly to your next lab, which is a projectile motion. Okay, so this the skill set and the amount involved is going to carry over. Okay? So this will be at the end of the class today. We'll come back and we'll revisit this reaction time lab. Okay, guys, look for a quiz coming up next Friday, so 8 days from now, Friday, which is going to be on linear motion and projectiles. So put it all together in one quiz. All right, so what's going on with the projectiles? I got an animation. Dig up this animation. All right, there you go. All right. So anything that's flying through the air, right, just under the influence of gravity. Right. So Splas's cannonball. Oh, hold on, my screen froze. All right, there we go. All right, here we go. All right, so actually, if I rewind a little bit, right there, here we go. So we're gonna blast a cannonball. It looks like, could V stand for velocity, which is like speed, but also there's a direction with this. It's like up and to the right. Could you quantify how many degrees from the horizontal that is? Right? So you could take a protractor and say, oh, it looks about like 40 degrees or something like that, right? From the horizontal. Right. Right. Now, guys, watch the motion of this cannonball through the air. Ooh, it's going up, it's kind of slowing down, then it's coming down faster, faster, faster. It's always moving to the right. Huh. It was going up, it's coming down, but it's always going to the right. Okay. And guys, what shape does that make through the air? Parabola. Yeah, that's a parabolic trajectory. Okay. Right. Now, you guys see those red and green arrows pop up? You see those? Right. Those are vector components. Ooh, you guys remember doing like some sine and some cosine a few weeks ago? Right. I know sine and cosine shows up all over the place in this class, and this is one of the first places, right, is to get vector components, which is going to help you make sense of this motion of this cannonball flying across the air. So, uh, so the total velocity is this orange vector marked V, right? Then if you break that into components, now when I draw components, I will always dash the components. So instead of the solid red and solid green, I'll just go dash, 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 and then dash, 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 dash. I will dash off those components. Okay. Also, I tend to make right triangles, or my components look like they make right triangles. So I would just take this green arrow and slide it over here, pop it in place right here. Can you guys imagine this could be like a right triangle? Right? That's what my notes will look like. Okay. Right. But once you got the components, let's focus on one at a time. You guys see this v sub x? Couldn't that be like the velocity in the x direction, like the horizontal velocity? Okay, so let's watch this motion again, but just focus on this red component that says v sub x. Watch what this is doing. Okay, there's a little jaggedy there. Oh, guys, is it speeding up, slowing down, or going the same speed in the horizontal direction? Yeah, same speed in the horizontal direction. That v sub x never changed all the way through, all the way through. That v sub x stayed the same. Right? Now, so why would that be? Well, um, is gravity pulling horizontally or only vertically? Yeah, gravity only pulls vertically, so gravity doesn't affect its side-to-side motion. That's true. Right. And there might be a little air drag, but haven't we been considering air drag to be negligible, or we just ignore it? Right. And if that's true, that means there would be no horizontal forces, so there's no horizontal acceleration. Yeah, it just coasts, right? Horizontally. If you were up in a hot air balloon looking down on the whole situation, you would pretty much perceive the horizontal motion of the ball, and it would look like it's just going pretty well constant speed just across the field. That's exactly what you would see. Right? That makes sense. Right? Right. Now, vertically, it's a different story. So let's rewind. Back at the beginning. Right. Let's look at this green component. Just the green component. Okay. So as it's going up, ooh, it's getting shorter, and oh, okay, now it's growing, but it's going down. Huh. Now, who can tell me? I bet some of you guys can figure this out. Who can tell me what is the rate change of that green component equal to? 10 meters per second squared. Yeah. It changes 10 meters per second every passing second. So if it started off, for example, going up at like 30 meters per second, I bet 1 second later it's going 20 meters per second, and then 1 second later 10 meters per second, and 1 second later, okay, so I'll drag it right, and then 1 second later going 0 meters per second. Oh, could that signify like the top location? Top location, right? Okay, and then it comes down 10 meters per second after 1 second, another 10 meters per second. Now we're up to 20. And then right when it's about to hit the ground, it's all the way up to 30 meters per second, right, in the vertical direction, just focusing on the green. Okay? Now, those components, that's a lot easier to handle than trying to figure out from scratch what's going on with the orange vector, right? Because that orange vector is like changing direction and changing magnitude all the time. Okay? Here, just to point that out, if you go back and look at the orange, isn't it getting shorter and change direction? Okay, now it's getting longer and it still continues to change direction. That's a mess. But those two components, that red and that green, those are a lot easier to work with because the red just stays the same and the green changes by 10 meters per second every second, right? Right? We can put that together, right? Sure. So let's do that. Let's give you guys some notes here. Notes page. So on big old sheet of paper, let's say here's a scenario. We're gonna blast a cannonball. Um, let's go 50 meters per second at 37 degrees to the horizontal. Okay, so that's the scenario. All right, we're on a big old plane, I'll draw the plane right here. Here's the ground. Zip. Okay. Sometimes it's common to like hash the ground like this, so there's something solid there. Solid ground. Okay. Put a cannon on the far left side of the paper. Just a little tiny cannon. And let's tip it up at, no, I'm saying 37 degrees. My picture's not going to be exactly the scale. I'm not going to measure this with a protractor. It goes, right. We're going to make believe that it's 37 degrees. You guys will see why this goes on. Okay. So, pow! I blocked that cannonball. And this has a magnitude of 50 meters per second. So if I point a radar gun at this cannonball right when it's leaving the cannon barrel, that radar gun reads 50 meters per second. That's okay, right? Right. Let's trace out the path of this ball. Okay, it goes like this. It's eventually going to come down. Right, something kind of like that. Right, make this parabolic trajectory. Makes sense. Right? Just like you guys saw in the animation. Right. Oh, I need to go and put my angle in here. Right, I'm going to break this 50 meters per second into components. Well, the cannonball's kind of going across the field, and it's kind of going up at the same time as it's leaving the cannon. And I'm calling this angle 37 degrees to the horizontal. So 37 degrees down the corner. Okay. Yeah. Right, you guys up to where I am in your notes? It's good. All right. Now, let's see. So I want to look at this cannonball at several points in its trajectory. I want to look at the very top point right there. I want to look at it right as it's about to hit the ground over here. Okay. And then a couple places, so like right here and here, going on the way up. Let's say like right here and right here, coming the way down. So you guys see like 7 cannonball snapshots with my 90s Strider camera. Okay. Let's say I was taking a picture every single second. Well, I've worked this out ahead of time, so I know if I took a picture every second, that's exactly where the cannonball would be. Okay. And I haven't told you exactly why, but as we go through the notes, you'll see why. It'll emerge why this takes 1, 2, 3, 4, 5, 6 seconds to hit the ground downfield. Okay. So, are you guys up to where I am? Okay, you guys good? Okay, so we got 1 cannonball at the blast point, and then 2, 3, 4, 5, 6, 7. So it's like time 0, 1, 2, 3, 4, 5, 6 seconds. Okay, so you guys saw the overall velocity, like the speed was slowing down. Okay, so you guys slowing down, can I represent that with a slightly shorter magnitude velocity vector? Right? And it's also constantly changing direction. Looks like it's shallowing out, shallower, shallower, shallower. And then once it crosses the peak point, now it's speeding up and the angle's getting steeper. Right? And so if I'm just focused on the overall velocity, I guess you might think from a like a okay, like the overall velocity and the speed you could read on a radar gun, but it will look something kind of like this. Okay. You see, I'm holding my ruler like flush to the parabola curve, flush to the curve, because that's the instantaneous direction that the cannonball is traveling. This instantaneous direction, like flush to the curve, okay. And then crash land, and just fit the center right here, yeah, pretty close. Okay. It's probably pretty good, pretty close model. Okay. Now those are all velocity vectors. Okay. Velocity vectors. You guys got all those velocity vectors? Okay. Let's break each of those velocity vectors into components. So I'm making a bunch of right triangles, right? Bunch of right triangles. I think that's pretty close. That looks pretty good. Right. Because again, to make sense of this, like the question could ultimately be like, if you're given this premise, 50 meters per second, 37 degrees from the horizontal, like, I wonder how far the cannonball goes. Right? I mean, that is an answerable question. You could eventually figure that out. You know how to approach this. All right, so let's go back to the last point and let's get some numbers. So how fast is the cannonball going across the field, like horizontally, leaving the cannon barrel? I'll call it V sub x, right? What's the velocity in the x direction? Okay. And how would I get that? Because V sub x is equal to what times what? Think back to trigonometry from a few weeks ago. The total blast speed is 50 meters per second. This angle's 37 degrees from the horizontal. How fast is it going across the field? Who remembers how to do that?
What times 50 times 37?
Yeah. 50 meters per second times cosine of 37 degrees. Yeah. Right. If you do that in your calculator, okay, so there's a specific reason I picked 37 degrees. I wonder if somebody remembers where you've seen that angle before in this class. 37 degrees. Does that ring a bell? 3-4-5 triangle. 3-4-5 geometry. Ah. So what's 50 cosine 37 degrees? That's 39.93. Let's call it 40. That's 40 meters per second. 40 meters per second. Really, this angle should be like 36.87 degrees or something like that, but I was rounded a little bit. Yeah, 40 meters per second going across the field. Right? And how about how fast is it going up the field? Or up. How fast vertical? I'll call it V initial in the y direction, or Vy naught, right? Because it's vertical, but it's only true for one instant. You guys know the vertical is always changing. Okay? So could that be 50 meters per second times what? Not cosine, but sine of 37 degrees, right? Isn't this leg of the triangle opposite of 37 degrees? That's why I'm bringing in sine. Okay. And if I scroll up, scroll over, and replace this cosine with a sine, right? Oh, before I hit enter, I bet so many of you guys know what it's already going to be. If it's a, what triangle again? Yeah, 3-4-5 right triangle. And I've got the hypotenuse is 5 times 10, which is 50. And this bottom leg is 4 times 10, which is 40. Then what's this side got to be? 30. 30 meters per second. Okay, let's see if it is. And 30 meters per second. Okay.
Or next to it says the something equals 50.
Yeah, that's v naught y. So that's initial velocity in the y direction.
Okay.
V naught y, initial velocity in the y direction. Okay. Because remember, the vertical component velocity is always changing. Okay. Actually, speaking of what it's doing down the field, let's put that together. Okay. Actually, I'll start with horizontal. We'll round back to vertical later. Okay. Horizontal. So remember how leaving the cannon, it was going 50 meters per second altogether, but 40 meters per second across the field. Right? How fast is it going strictly across the field 1 second later? Let's say, what is this component right here? Yeah, 40 meters per second. How about 1 second later? How fast across the field? 40 meters per second. How about, guys, at the very peak of its motion, it's moving to the side. How fast? 40 meters per second. Is it 40 all the way across? 40 meters per second. 40 meters per second. 40 meters per second. That never changes. As long as it's in free fall, as long as it's a projectile in the air. All right, you guys ready for a vertical? So, yeah, leaving the cannon barrel strictly in the vertical, it was going 30 meters per second straight up. Right? Kind of like if you just took a ball, you threw the ball straight up at 30 meters per second. Right? Ooh, did that premise show up yesterday or Kahoot a few times? You throw a ball straight up at 30 meters per second? You guys remember that? Yeah, buried somewhere in my notes. So after 1 second, now it's going up how fast? 20 meters per second. And after 1 more second, it's going up how fast? 10 meters per second. 1 more second, up how fast? 0 meters per second. Right? No, that's strictly vertical, right? It's still going to the side. That's okay. Right? But it's not moving up or down just for that one moment where it's at the very top. Right? It's like turning around. See how 30, 20, 10. See how it's losing 10 meters per second every second? Because gravity's pulling it down at 10 meters per second squared. Right? Is that what that is? All right, so picking up from the peak after 1 second. Now it's kind of going down. Oh, now it's picking up speed. How fast is it going strictly down? 10 meters per second. After 1 more second, how fast down? 20 meters per second, and then meters per second. Right? Sure? Good. So now we can make sense of this. The horizontal motion just stays the same all the way across, 40 meters per second. The vertical motion changes. So it changes by 10 meters per second every second, and it tends toward the ground, which is the way that gravity's pulling. Okay. Last question here. It ties it all together. When this ball is just about to hit the ground, say it's like 2 millimeters above the ground, it's just about to crash land. Somebody points a radar gun at that ball. What does the radar gun read? How fast is it going right here?
40 meters per second.
Well, it was going 40 across, but it's also coming down at 30. Put together, that makes what? Huh?
70?
40 across, 30 down. It's not 70. Guys, how do you add right angles together? Pythagorean theorem. Pythagorean theorem, right? Let's see, 40, 30. Hey, looks like we have another what triangle? 3, 4, 5, 30, 40, 50 meters per second. Okay. Okay, so if you do Pythagorean theorem, right? Or you could have done this by symmetry. Do you remember the blast speed, which was also at ground level, basically, was 50 meters per second to start with? It's slowing down on the way up. It's speeding up on the way down. You guys see by symmetry, of course, it would be at the same speed at equal elevation. Okay, so do. Okay, so. Okay. All right. So let's do some posters. Get ready for posters. Okay. So would you guys believe that this whole example we just did was hanging from my ceiling the whole time? Oh yeah, look at that. That's this one. We just did this. You guys just put all this in your notes, didn't you? Got that. It's hanging from my ceiling back there. It's right there. Projectile. Oh. So you guys have that. You put them on notes. Okay. This is one classic category of projectiles. If you start on the ground, you're on a big old plane, big old field, and you just blast a cannonball. Maybe you want to know like where does it land or something like that. That could be a question. Okay. Another category question, which is going to look a lot like a lab that you're going to do a few days from now, is if you're sitting a cannon on a cliff, and maybe you just aim the cannon straight horizontal to keep it simple, right? It's like that. A few days from now, we're going to go outside. I got some launchers, and I have little squishy bouncy balls. And you have 5 bouncy balls, and you're going to land somewhere down here, or fire them off the balcony. Okay. Now, let's play around. How about this? Because what shape is this right here? What shape? Parabola. Aha. And the vertex, would the vertex be right up here at the top? Okay. What if you turned gravity off? Boom. There's no gravity. You lost it. What does it do? Yeah, straight line. Just keep going straight line. It doesn't hit the ground at all. Right? What if you turn gravity way up? Oh, it feels so heavy. What does it do?
It goes straight.
Shoot, plunk. Yeah, it might go in. Yeah, maybe about here. It doesn't go very far. Right. Right. How about? All right, let's go back to regular gravity. What if you change the blast speed? What if you blast it really fast? Where does it go?
It goes.
Yeah, way out here. Maybe off the paper. Maybe. Right. What if you um? What if you change the height of the cliff? What if you make the cliff really short? What if the cliff's down here? Where does it land? Phew. I bet it doesn't go very far. What if you have a super tall cliff? Now is it maybe leave the paper again? Right? Okay, so we're juggling all these variables. Gravity, like where does the ball land? So when you do this experiment in a few days, you're gonna blast the ball, it's gonna land, you can spot where the ball lands. Can you take a meter stick and measure? Can you walk up the stairs and measure like 1, 2, 3, 4 meters? Can you do that? Measure the height of that balcony out there with a meter stick? Okay. Can you take either a meter stick or a trundle wheel and measure how many meters out your bouncy ball lands? Okay. And big picture here. I want you guys to think big picture. Do you think, in principle, if you know the height of this balcony, you spot where the ball lands, and you know Earth's gravity field, let's say you're allowed to use G as 10 meters per second squared, is there enough information there that, in principle, you can calculate the blast speed of your launcher?
Yeah.
Do you do that? Yeah, because that's going to be your task. So I want to plant that idea today. You have a few days to think about it. Right? Right, so here's a big picture: is in the horizontal direction. Guys, for all these projectiles, there's only one horizontal equation: x equals vt. That's it, because there's no acceleration. So if there's no acceleration, it's just distance equals v times time. That's it. That's all. Right. Now in the vertical direction, it depends what's being asked. Because in the vertical direction, now you're back to an accelerating environment because gravity pulls straight down, doesn't it? So now you're back to these three amigos. And if you're interested in height as a function of time, some version of the first one, okay, you guys see this y equals 1/2 gt squared right here. Okay. So oftentimes for the next few days, I'll call a vertical displacement either y or h sometimes for height change. Okay. Good. All right, so what can we do with this? Oh, look what I got for you guys. Got the answer to your next lab. So I'll show this, and then when you're out there putting it together, see how much of this you remember. But here's the game plan. Oh, here. All right, here's the game plan. Is you have a cannon on the balcony, launch on the balcony. Right, you launch the ball, see where it lands. Okay. Now there's a vertical part of the story, and there's a horizontal part of the story. All the vertical I put in red, all the horizontal I put in green. You see that? Okay. Now the vertical, what am I doing? Okay, so I got that first kinematic equation basically. And as long as you blast it straight horizontal, guys, if you blast it straight horizontal, then when the ball's leaving the launcher, is it moving up, down, or neither up nor down? How about neither up nor down, just for the first instant? That's why there's no initial velocity here, right? Okay, would this be the same? Would this right here? Would this be the same as if you just drop the ball, like, oh, it fell off the edge, what? And you blast one at the same time. You blast the ball and you drop the ball at the same time. Which hits the ground first? Same time. That's right, same time. That's right, same time. I'll show that to you guys tomorrow. I got a video of that happening. Right, so I'd like to know how much time it takes to reach the ground. Because if I know how much time it takes to reach the ground, I can very simply say, well, how far it goes horizontally, divided by that time, tells you how fast it's going across the field, therefore the blast speed. You guys see that would be the same thing? Right? Therefore, you can get the blast speed strictly in terms of the height of the balcony, how far the ball lands, and the gravity of the plane. That's all. Right? Notice they don't have a stopwatch here. Right? So you use a stopwatch to figure out how much time? They're like, okay, launch and hit. Is that very good? Is that very accurate? All right, probably not very accurate. Right? Not as accurate as this method is ready, where you're calculating based on drop height. Right? You can also, guys, this one's a little different. If you know what your blast speed is, could you in principle predict where the ball's going to land? Right? That's what this one's for. It's a little bit different than what I just showed you. This one's fun. I might save this one for a different day. But if you know the launch speed, you know this angle, and you know the gravity field, do you think in principle there's definitely some location downfield that ball will land? Right. Now there's a whole process. Actually, it's not too bad. This is the whole process here. Right. It's kind of small ink. Right. But this ends up being the end result. Ends up being this equation. So we might round back to this in a few days, possibly. I don't know. We'll see. Right. And then, at some point today, I want to do this with you guys. So let's do this. Let's switch over to your guys' puzzles. Right. You guys got some puzzles here. I just gave you guys these. Help you guys make sense of these. Okay. So there are 6 scenarios on the front side. The 3 on the left all involve cannons firing horizontally at the edge of the cliff, which, by the way, is the same as this picture right here. So the 3 scenarios on the left, you can use this picture. Okay, cannon on a cliff, blasting horizontally. That's okay. And I gave you some information, and I have lots of different types of questions. Okay. Now, once you have enough information, you can solve everything else. Do you see how I split the table sort of in 2 parts? There's a left half of the table and the right half of the table. Is that right? The left half of the table refers to horizontal information. In fact, you might want to label that. You guys see I got that labeled horizontal, and I got the right table labeled vertical. So that there's a left side and a right side. Okay. Because you have to keep track of different axes, different dimensions. Right. Okay. Right. So, right. And horizontally, ooh, guys, horizontally, there's no acceleration. All it is distance equals speed times time. That's all you're doing horizontally speaking. Distance equals speed times time. That's it. Right. Now vertically, well, vertically is a little trickier. There's more involved because there is gravity vertically. Right. So, oh, look, I have that labeled right here. Acceleration is 9.8 meters per second squared. Looks like we're on Earth. Right. You guys get that? Right. Now there's one variable that is allowed to be transferred from horizontal to vertical or vice versa. Right. And it's the value that's a scalar as opposed to a vector. Guys, out of time, acceleration, displacement, and velocity, which is the only vector that is a scalar? Which one? Which one does not have a spatial direction to it? Time. Right. So here's what I mean. There's the amount of time that the ball takes to get from here to here. Is that the same regardless of whether you analyze it vertically or horizontally? Is it the same time to get from here to here? It's the same time. It's the same time. Okay? So the reason I'm setting up this tables this way is to help you organize this information. But however much time it takes to go across is the exact same time it takes to fall. You can transfer this time from here to here. Okay? Same thing when we go over here. Whatever the time is you're allowed to transfer that. Okay? Same number of seconds. Okay? Right, so help you keep track of what's going on vertical, what's going on horizontal. Right? So we do those. Right? These questions on the right side, are a different scenario. This is all you're on a big old plane. You have the cannon ramped up its own angle, and you're blasting a cannonball on a giant plane, which is basically this picture right here. So this picture right here, you can apply to these 3 scenarios on the right side. Of course, they give you different kinds of information starting out. Okay? Here's a fun detail. Guys, look at this bottom left, this bottom one on the left. A cannon fires a cannonball horizontally, given speed, off the edge of a cliff. Okay, so we know the blast speed on a cliff of given height. Okay, so we know the cliff height. On an alien planet, guys, if you're on an alien planet, you might not immediately know the what?
Gravity.
The gravity field. In fact, I did not give you the gravity field. You see, acceleration is left blank. Okay, so just, that one's kind of fun. On the backside of this page, we got, kind of a hybrid. Yes, there's a cannon on the cliff, but also it's ramped up its own angle. All right, so that adds a little bit of complexity to it. Right, so not blasting horizontal. Okay. So the scenario on the left, I guide you guys through. So if you go step by step, it'll guide you guys exactly through. And in fact, they gave you some multiple choices to make sure you're on the right track. Okay. The ones on the right side are basically the same premise. They're just a little bit more open-ended. Right, so so that's going to be our adventure next few days. So tomorrow I might show you guys a demo or 2, but basically I want to full focus on this page tomorrow, and then the next few days we'll be doing this, and of course I'll build it in the lab also. We'll go outside with the launchers at some point. Okay, and then this page is due on what did I say? Did I say Thursday? Wait a minute. Well, I guess that's the soonest I would pick it up. I won't pick it up before Thursday. Right, that's the soonest I would pick it up. I'll see. I might bump that a day. I'll see. Right. Okay. Any questions so far about big picture? Okay. So far I haven't even really solved any of these with you guys. We'll do that tomorrow. But I just want to focus big picture. Okay. But there's still one I want to go back and revisit. Where'd it go? How do we put? Here it is. Here it is. Right. Reaction time. Okay. So let me get you guys a paper right here. Right. So you guys got a ruler nearby. I want you guys to figure out what is your reaction time. You need a partner to do this. So let's make basically this table right here. I'll draw it with you guys. So write your name. Write your name. Call us reaction time lab. Reaction time lab. Okay. Yes, if you're trying to figure out what's your reaction time, do you want to use the stopwatch? Like here, catch, start, stop. Oh, is that going to solve reaction time very well? No, because trying to figure out when to start and stop the stopwatch is kind of the question we're getting at. Is sort of what's the delay between reality in the world and your brain perceiving that reality? Right? You're driving your car, a deer steps out in front of the car. You're not going to immediately step on the brake because you need time to process that. How much time? You're going to find out today. There's a much more accurate way to figure this out, and that's using this ruler right here. So you have a table. Let's go make some column headings here. Okay. So we've got various trials and how far did the ruler fall? I'll call it H for like a height change, and how much time. Okay. So there's some units that go with these two. Trial units could be trial A, trial B, trial C. You can call it trial 1, 2, 3. Okay, so different trials. Right. You probably want to do 3 and take an average. Okay. Maybe at the end of this, you want to do like an average here. Do AVG for average, something like that. Okay. Now, height is going to be in some units, and time is going to be in some units. I want to sort of leave this to you guys, but the height you're going to measure just by dropping the ruler, and the time I want you to calculate. Okay, like this. So you and a friend pair up. Okay, let's say your friend's holding the ruler, and you have your fingers at the 0 centimeter mark. You see 0 centimeters here? Okay. Your friend drops the ruler. You catch it as fast as you can. Okay. Now, guys, while the ruler is falling, is it accelerating? Mm-hmm. Yes, it is accelerating, right? It is accelerating. And if it's accelerating, it's falling faster, faster, faster. Do you guys think that the amount of time that the roller's been falling for can exactly be determined by how far it's fallen? Okay. Right. Here, I'll really help you guys out. Okay. Which kinematic formula tells you the relationship between distance fallen and the corresponding time? Yeah. You guys are saying the first one? First one? Okay. This is the one that has the X and the T in it. Okay. This one doesn't say how far it fell. This one doesn't say anything about time. Okay. It's got to be this one. And because if you drop the ruler, or your friend, who's here? You drop the ruler, your friend drops the ruler. How can you simplify this? What goes to 0? Yeah, initial velocity. So that term goes away. Hey, look what we have. It's the college equation. College. You guys remember college equation? Okay. Fell for 5, 6, 145 meters to college. That's okay. But you guys are going to turn this around. You're going to solve for how much time has the ruler been falling based on how far did it fall. True? Is that okay? Do you just want me to show you the algebra on that, or do you want to solve the algebra? Can you guys get it from there? Get it from there? All right. So here, I'll let you guys do it. Now, there's a couple of really common mistakes that are made on this, so I'm going to walk around and make sure that your numbers look accurate. If your numbers look accurate, you can turn this into the grade tray into class, and you're good to go. You guys got lab points. If it looks like you're doing something wrong, well, I'll at least tell you that, maybe throw you guys a hint. All right, so go ahead. I'm going to close down this recording, walk around, and make sure you guys are able to do this all right.